the region bounded by those parabolas. So at least you get nice parabolas, right? Yay, nice parabolas. Okay. So y equals x squared. You know what that looks like. And again, are you looking for total exactness on this? So we have y equals x squared, and then you have y equals 2 minus x squared. Very similar thing, but it's at 0, 2. And then what's it going to go? Oh, down. Like this, right? Yay. Find the volume of the solid if the cross-section perpendicular to the x-axis are squares with one side lying on the base. So cross-section perpendicular to the x-axis would be a cross-section like that. Can you see the yellow? Good. You can see it. So at each of those cross-sections, this right here, from here to here, this is the base of a square. See the square, everybody? Oh, I'm sorry. I just killed it by drawing too many. Ah! Do you see what I'm trying to erase? There we go. So this right here is a square. And imagine this moves. I keep on doing too many lines. This moves side to side. So do you see the square right there? So the square, if I did it here, is going to be bigger. Do you see that right there? How do you find the volume of a square that has a little tiny depth? Well, is this a dx or dy? Dx. And we're going to go from left, what's this x value, all the way to here. What's that x value? So where do these intersect? -1 and 1. So we have -1 to 1. And what's the area of a square? Side squared, base times height. But this base and height are the same, right? So in this case, it's going to be the side in terms of x squared. So side squared x. And what is the depth? What's the thickness? Dx. That's all you're evaluating here. And in this case, how do you find the height? How do you find the side length? How do you find the side length? It's right there in front of you. The upper function minus the lower function. What's the upper function? 2 minus x squared minus what? X squared. And you're going from -1 to, and it's dx. So if you're gonna do this by hand, oh, and it's squared. Thank you very much. And it's squared. Thank you. That's very important. Yeah, so what you can do right here, so you end up with 2 minus 2x squared dx, right? And is that something you could integrate right there? Due to symmetry, you could change this to what? 2 times what? 2 times the integral from 0 to 1 of 2 minus 2x squared dx. So if you had to do it by hand, that would help. If you go across a squared, you could. You have to be very, very, very careful about that. If you pulled it out, what would it be? What would it be? You'd be very careful. I mean, you can think about it and do it yourself, but just be careful, okay? It'd be easier, honestly, just multiply it out so you don't make some really, really simple algebraic mistake. I'm going to give you the same base. Same base. Nice, nice base, yep. So I'm going to give you y equals x squared, like this. And then I'm going to have the upper bound be the same thing, so it goes down like this. A little better, y equals 2 minus x squared. Instead of the cross, so the cross sections will be perpendicular to the x-axis, so you have a cross section like this. But instead of a square, I'm going to make it a semicircle. So what would this one look like if it was here? You kind of see what that looks like? It's hard to see because I did the angle a little too steep. Let's say it was a semicircle like this. And that's a semicircle. So the question is, what is that volume? But first, set up the integral. See if you can set up the integral for that. For semicircle, 1/2 pi times r squared. Okay, so these slices right here, is it going to be dx or dy? Dx. So you need the radius in terms of x, correct? Okay. So what are you integrating from and to? Do 0 to 1, yeah. And what are you're going to double it, right? So it's going to be doubling 1/2 pi r squared dx. But what's missing? What's the key thing you have to figure out? What is r in terms of x? What is r in terms of x? So the best way to find r in terms of x is to literally draw it first. The radius goes from the center all the way down, correct? It's just 1/2 of, again, but what is this middle always at right here? What is that? That's y equals what? 1. But look, the radius changes, correct? The radius changes. So what's that bottom function right there? What's that red one? X squared, exactly. So what's the radius going to be? Radius in terms of x is going to be 1 minus what? Yeah, it's just 1 minus x squared. Exactly. So what's this integral going to be? 2 times the integral from 0 to 1 of 1/2 pi times 1 minus x squared, and this whole pi, 1/2 pi r squared dx. Does this simplify pretty nicely? Mm-hmm. 2 and the 1/2 cancel into with pi 0 to 1 of 1 minus x squared dx. This is definitely something you could see on a multiple choice test. It could say set up but don't evaluate. It's enough. It shows you have to know pretty fundamental calculus in order to set up this integral. What's a great thing to do first? Draw a picture. Yeah, look in the back of the book. Let R be the region bounded by the curves y equals tan, x squared, x equals 1, and y equals 0. Use the midpoint rule with n equals 4. What does midpoint rule with n equal 4 mean? How many divisions? How many divisions? 4 divisions. How many rectangles are you finding the areas of? 4 of them, right? So here's the thing. You don't even have to draw a picture if you don't want to. The point is you're doing the midpoint rule, and you're going from 0 all the way to what? 0 all the way to what? 1. So if you were to break... Oh, that was a bad straight line. If you were to break this into 4 equal pieces, what are you at? 1/4, 1/2, and 3/4. So if you were doing right-hand rule, you would use 1/4, 1/2, 3/4, and 1 as the x values of your the right-hand side of each rectangle. But we're not. We're using the midpoint rule. So where are our midpoints? Here, which is what? 1/8, and then 3/8, and then 5/8, and then 7/8. Each rectangle's height is done. So the first rectangle is here. There's another one. I'll switch this up. So these right here represent the bases of each rectangle. How do you find the height of each of these rectangles? It goes up to f of 1/8. It goes up to f of 3/8. It goes up to f of 5/8, and it goes up to f of what? 7/8. What's the width of each of these rectangles? What's the width of each of them? So it's 1/4 times f of 1/8 plus f of 3/8 plus f of 5/8 plus f of 7/8. Is this something you think you're going to have a calculator for? Okay, so let R be the region bounded by the curves. Use the midpoint rule to estimate the following: the area of R and the volume obtained by rotating R around the x-axis. So this is A right here. You're going to use like this, I think. And I'm not going to ask you this one, so you can kind of forget about this. But you have these rectangles. You don't know how high they are, right? It might look like this. Do you agree? What they're saying is, so the function might look something like this. Do you agree? What they're saying is, if you took those rectangles and rotated them, if you took those rectangles, Jason, and rotated them, it would give you an estimate for the area. The integral, when you actually do the integral, you get the exact volume. If you rotate the rectangles, these 4 of them, you'd have an estimate for the volume. I think that's what they want you to do. Let's just skip over that because I'm not going to ask you to do that. That's totally fine. If you could do that if you wanted to, you could find, so if you took this one right here and rotated it, you see what I'm saying? Like you would rotate there. That's a really poor rotation right there. But if you had this one and you rotated it, you see what I mean by this rotation? So you rotate one of them. That's just a cylinder, right? Do you know how to find the volume of a cylinder? So then you do it 4 times and add them together. It's just kind of annoying, especially since you could find the exact volume if you wanted to with your calculator.